Welcome everyone to another lesson on Khadija Academy. Before we start this lesson, hit the subscribe button, the notification bell, and the like button for the YouTube algorithm. Now let's go and start our lesson. Hi and welcome everyone to our video on residual current circuit breaker. In this video, you are gonna learn all what you need to know about RCCBs from A to Z. You are gonna learn everything you need to know, including the working principles and the manufacturer specs. So the contents of this lesson will be as follows. Number one, we're gonna have an introduction to RCCB. Then we are gonna discuss the working principle of a single phase RCCB, the manufacturer specifications of the single phase, the working principle of a three-phase, and finally the manufacturer specification of a three-phase RCCB. So let's start by the first question, is that why do we need residual current circuit breakers? These type of circuit breakers are used to disconnect the power supply when it detects a leakage current to the ground. So if there is a leakage current, to protect leakage current due to insulation failure or accidental contact with a live conductor or whatever, we use RCCBs to detect this problem and then disconnects our supply in order to protect human beings. So it plays a vital role in preventing electric shocks and reducing fire risks caused by earth faults. So let's see how does a single phase RCCB works. So under normal conditions, the current entering the load via the phase wire equals the current returning through the neutral line. So if you look at this circuit breaker, the RCCB, a single phase, you can see we have a line and a neutral. So for example, the entering line and the neutral. And then we have number two, which is a line going to the load. And we have the neutral coming back from the load like this. So this is the neutral coming from our load like this and returning back. So the current enters and goes to the load, let's say for example a resistance like this, and then comes back like this and comes back through the neutral back like this. So under normal condition we have current IL1, which is the phase current, and we have I neutral. So if we are in normal condition, the current entering going to the load equal to the current coming back. So in normal condition, IL, the line current, should be equal to I neutral. So what do we even mean? It means that IL minus IN would be equal to 0 in normal conditions, because there is no leakage current. So if there is a leakage current, some current goes like this to anywhere like this, I leakage, then you will find that the neutral current coming back will be smaller than IN, would be smaller than IL. So there will be a difference. It will be IL minus IN will not be equal to 0. In this case, we have a leakage current. So any difference in these currents indicates that there is a leakage current, meaning that often means that this current is flowing through a person to the ground. So I leakage, which activates our circuit breaker, is equal to I line minus I neutral, the current entering minus the current returning back. Now, if this current as an absolute value is greater than or equal the trip threshold, this threshold is the minimum current at which this circuit breaker will be activated. As an example, 30 milliamperes. This is the value. If this one is 30 milliamperes, if the difference here exceeds 30 milliamperes, this circuit breaker will be activated or trips. Now, why it is a very small value? Because this small value can be harmful to human beings. That's why with a very small leakage current, we start activating our breaker. Let's see another diagram. So here we have line, I line, and this is the neutral, I neutral. And this is our RCCB. So here I line, it goes like this to our load and then returns back. If there is a small leakage current going through a human being like this, so if the current is 10 ampere, the returning current will not be 10 ampere because there is some leakage current here. This some leakage current will make the neutral current smaller, 9.996 for example. So if there is a difference between here, this RCCB will be activated. Now let's understand how does it exactly do this. So this is a diagram of what happens exactly inside the circuit breaker. So we have, this is the line and this one representing the neutral. So forget about this purple line for now. Forget about this one for now. This is for testing and we are gonna talk about this later. Here we have, this is a line entering like here, entering here, and then inside, this is inside all of this, inside here, all of this is inside our breaker, okay, all of this, and then this is the leaving going to the load, okay, so this is the leaving, and then we have the return path, this path coming back for the neutral, and this is also coming back for the neutral like this. Now as you can see, we have two coils. We have here a toroid. This toroid here is simply a ring. You can think of this as a ring. Now what happens is this, when this current goes like this, if you apply the magnetic field rules, like for example the Fleming right hand rule, you will find that the magnetic field will be in this direction like this. Okay, when this current goes like this and gets back like this, it will go here like this, going like this, and gets back like this. So if you apply again the right hand rule, you will get a magnetic field in this direction like this. Now you can see that we have another coil here called the secondary coil. So we will have a magnetic field flowing like this in this direction, and another magnetic field coming from the due to the neutral in this direction. So if I line equal to I neutral, then what happened? These two magnetic fields will oppose each other and cancel each other. So it means that there will no current flowing in this one. There is no induced EMF. What if IL greater than I neutral due to any leakage current? In this case, what will happen is that this magnetic field will be stronger than the magnetic field coming from the neutral. So there will be net magnetic flux. This net magnetic flux will induce an EMF here on this coil, the secondary coil, leading to flow of current. And if this current is strong enough, leading, for example, to I leakage greater than 30 milliamperes, in this case, this coil here will be able to trip the circuit breaker. It will make it open like this, produce a force, magnetic force, that will open these contacts. Okay, so this is how it works. So number one, the orange wire representing the live or phase current, carrying the current to the load. The black wire representing the neutral, coming back from the load. And you'll find that the blue wire called part of the trip circuit called containing the secondary or sensing coil H. This secondary coil that will activate or trip this circuit breaker. Now the last one, which is this one, which you will need to do frequently if you have this type of circuit breakers. This one is called the test part. This contact here, which will have a push button like this. When you press this push button, it will make this one a short circuit. It will close this contact. This push button is this one, which is a test. Now what does it do? When you close this circuit like this by pressing this button, you will see there will be a short circuit. The current will go like this and flow in this direction, and then it will return back like this. So what happened in this case? You will see that the current, let me just delete all of this. The current flows like this, okay, goes like this, okay, like this. Now you can see the current IL equal to 0, right? No current flowing here. There is no current flowing here, right? IL equal to 0. And the total current here, the total current will go like this and return back here. So this one will produce a magnetic field, right? Magnetic field. This one is 0. So in this case, we will have a net magnetic field leading to activation of our switch. So this one, when you test, if you would like to test it in order to make sure this one is working properly. Now, why do we have a resistance? Because if we don't have a resistance, look carefully what will happen. We will have line connected directly to the neutral. There is no resistance, so you will make a short circuit, right? Which you don't want. You add here a resistance in order to make it a controllable leakage current, a small leakage current, in order to make sure our RCCB working properly. As you can see here, it includes the resistance, which limits the currents and simulates a controlled leakage current. Now let's look at the specs of the manufacturer. You can see here we have some specs on this circuit breaker. You can see we have IN equal to 40 amperes. This one, IN equal to 40 amperes. What does this mean? N refers to nominal current. Or in another way, we can say the rated current. This is the current that it can withstand for a long time, continuously, without overheating. The maximum continuous current the RCCB can handle without overheating. For example, here 40 amperes, it means the rated current 40 amperes. This is the first value. Second one, you can see I delta N. Delta, in order to make it easier, any delta refers to residual. So the nominal residual current or rated residual operating current, you can see 30 milliamperes. What does this value even mean? It means our circuit breaker will activate if the leakage current equal to or greater than 30 milliamperes. You can see sensitivity. It will trip if it detects a leakage current greater than or equal 30 milliamperes. The next one, INC. You can see IN nominal and C means conditional. So conditional short circuit current. And this one means I conditional also, but residual. So it is conditional short circuit current rating for this one, and conditional residual short circuit current rating. So if the short circuit, in case of a residual or a short circuit in normal operation, maximum value that it can withstand is 10 kiloamperes. So you can see RCB can withstand short circuit current up to 10,000 amperes. Now remember, this one only protects against leakage current or air fault leakage current. However, this type is not used as a short circuit protection. You have to use this along with a miniature circuit breaker or a molded case circuit breaker. So you need another circuit breaker. This one is used for short circuit protection. You can see it doesn't break short circuit current, but it must survive it. Now we have UN, nominal voltage, 230 volt, and this symbol which is called tilde. So tilde here you can see it is similar to a sine wave, it meaning that this is an AC supply, AC. And 230 volt, this is a nominal voltage or rated voltage. So it means that this is designed for a line to neutral voltage of 230 volt. You can see it's designed for a 230 volt AC system. IM. M means making. Making means that it means it can open, it means that it can close, or I break, which means break the circuit, break or close with the current existing. Making capacity is 500 amperes, the maximum instantaneous current that safely interrupt without damage. Now we have another sign which is called CE, this one, which had this abbreviation. And what does this mean in English? In English it means European conformity, if I remember, conformity, European conformity, or confirmation by European standards. So you can see the product complies with the European Union quality standards. Now the symbol here, this one beside the 30 milliamperes, here exactly, this one here. In this one you will see a small box. Okay, let me just zoom in like this. As you can see, there is a symbol of the sine wave inside a box like this, like this. So what does this even mean? It means this is a type AC RCCB. This one is used only for AC residual currents, only AC system. It cannot be used for DC or a pulsed DC. And this is what we use usually in household installations. Now there are three types which I'm gonna show you right now. So we have three types of RCCB. Type AC with this symbol, it means it can be used only for a pure sinusoidal AC leakage current only. This one, type A, it can be used for two, AC as before, and pulsating DC leakage. Now what does this even mean? When you have a rectifier, like a single phase rectifier, the output will be like this. It can be pulsating like this for a full bridge, or it can be pulsating like this for a half bridge, as we discussed before in our course for power electronics. So in case of this one or in this one, this type A can be used for a AC leakage sinusoidal or a pulsating DC leakage coming from rectifiers, variable frequency drivers and dimmers. Now type B is used for this and the pure DC. So you can see AC, pulsating DC, or a smooth DC leakage like this one here. This one is used in industrial machinery, medical equipment, electric vehicles, fast chargers, and so on. So these are the different types or symbols which you can see on the circuit breakers. Now the three-phase system is similar as the single phase. We have A, B, C, three phase and neutral, or L1, L2, L3 and the neutral, and we have 1, 2, 3, the one which are going to the load and the neutral coming from the load. Now if you look carefully here at the specs, it is almost similar. I nominal 40 amperes, I delta N 30 milliamperes, and so on. The only difference is UN, or the nominal voltage, 400 volt. What does this even mean? It means 400 volt line to line voltage. So it operates at a nominal line to line voltage 400 volt. This is the only difference between these two. Now, what does this do or how it works? You can see we have the three-phase input and the neutral going to a current sensor or a current transformer. So it has the three as an input. You can see this one, and this is pretty important. It sees them as like this. It looks like I1, I2, I3, and I4. So what does this N, IN. So this coil, what does it see? It sees the summation of current. So this coil looks at summation of currents. So it looks at summation I1 plus I2 plus I3 plus I neutral. If this summation is equal to 0, it means normal operation. If this one does not equal to 0, it means we have a fault. Now, why does it sum like this? Because this is a coil. It looks them like this. Now, what about the neutral? The neutral comes back in the opposite direction. So the neutral, you can see L1, L2, L3, and this is the neutral. So it comes back like this, and this is I1, I2, I3. So as a vector, you will see that IN itself will have a negative sign due to the opposite direction. So it has a already negative sign inside it. So what I mean by this, if we know that the summation of currents in a three-phase equal to I neutral, right? So I1 plus I2 plus I3 equal to I neutral. If we have a balanced three-phase, it means that this summation equal to 0 and I neutral 0 in a balanced system. So 0 plus 0 meaning 0, so we are in normal operation. If we are in unbalanced system, then the summation, let's say this summation is 8 amperes, then the I neutral will be 8. So this part will be 8 amperes. This part will be negative 8 amperes. Now you are gonna ask me why there is a negative here, because the I neutral, you can see it goes in the opposite direction. So it has a negative sign due to its opposite generated magnetic field. Now the summation of these four currents will lead to a magnetic field. If there is a net magnetic field due to a fault, it will be activate a coil that will open or trip the circuit breaker. Now this part specifically, the magnetic field, permanent magnet, why do we have this? This one is used to control the residual current value. So when we say 30 milliamperes, it is dependent on the magnetic field here and other properties. Now I discussed this in details in our course for protection, so I'm not gonna repeat this part for now in details, okay? Now for now, let's look at here. So we have, let's delete this. In three-phase, RCCB monitors all the three-phase and neutral. And you can see that I leakage will be summation of currents plus I neutral. If the I leakage greater than a threshold value, then RCCB trips, same as before. Now if you look at the construction of this one, how does it look like? We have a current transformer like this one. You can see L1, L2, L3 and the neutral. All of them are surrounded through this current transformer flowing like this, like the wire is around this coil transformer like this. So when the current goes like this, and you can see I neutral comes from the opposite direction, you will see the magnetic field of this will be opposite to the magnetic field of the neutral. The net magnetic field will flow through this, will affect this coil. If there is a net magnetic field, we will have induced EMF here, leading to generation of current and so on, the same process. This is for the three-phase configuration. Now let's look at the last step, which is the properties of our or manufacturer specs. Now these are the specs which I obtained from the manufacturer of this circuit breaker, and unfortunately there was some mistakes in the specs itself. For example, this one and this one and this one were missing their delta sign. So what does this mean? You can see rated residual current should have delta because IN is the rated current or the nominal current. Now you can see I delta N, it should be I delta N. In the manufacturer website itself, it was written as IN, same as rated current. So if this one was a mistake on the website, any residual should have a small delta sign. Similarly, here you can see rated short circuit current and rated conditional residual short circuit current. Any residual should have its own delta. Making and the breaking also has a delta. Now if you look at this one, voltage here, UN, 400 volt AC, 3 phase, 3 poles, L1, L2, L3, and the neutral. The frequency of operation, the rated current. This breaker has two ratings, can be found in the manufacturer, 40 amperes and 63 amperes. Now if you go down here, residual currents which we discussed before, 30 and 100 milliampere, these are exist for 40 and 30, 100, 300 for 63. So it has a different ratings for residual currents. And here these are the short circuit in case of an earth leakage or in case of a normal short circuit. This is the maximum value it can withstand. Now rated and the making breaking capacity IM, it means that it can interrupt or close a circuit when a current of up to 500 amperes or 10 times I nominal, whichever is greater. As an example, if we are talking about the 40 amperes, it will be 10 multiplied by 40, giving us 400 amperes. In this case, its rating will be 500. In another case, for 63, it will be 63 multiplied by 10, 630 amperes. So in this case, the breaking and the making capacity will be 630 because it is the greater value. Similarly, you can see type AC. It means that this one is used for sinusoidal, and this is the temperature at which it can operate. I hope this video helped you understand the residual current circuit breakers. And if you like this video, don't forget to subscribe to our channel for more electrical lessons.